Hi everyone. In this Connect with Networking video, we're going to be discussing Chapter 7, Wired and Wireless Local Area Networks. Let's go ahead and get started. Most businesses, both large and small, are predicated upon each individual user being connected to a local area network. And there are lots of reasons for doing so. And the most common, of course, for most people when they first think about connecting to a local area network is not actually the local area network itself. It's using a local area network to connect to the internet and broader resources. But there are lots of reasons to only have a local area network. Information sharing between individuals that work for your company allow for the reduction of data duplication and make it easier to resolve any inconsistencies. We can share resources like printers and file shares. We can potentially share software where the license can be based on a per seat basis and the software actually resides on the server. And we can manage our devices from a central location. So software updates and configuration can be managed by the network administrator and not left to the devices of the individual users. When we think about local area networks, we have to consider both the wired side and the wireless side. The devices that are going to be connecting to each other are clients and servers. And the way that these devices are connecting to the network is typically through a network interface card. Most network interface cards are now integrated into the motherboard of your desktop or your laptop. But in some cases, you can have an add-on daughterboard network interface card with additional features. If your device is connecting to a local area network via a wire, it is likely connecting through a hub or a switch. If your device is connecting to your network wirelessly, it's connecting via an access point. And of course, there is software that goes hand in hand with these hardware devices to allow all of this to operate up and down the network stack. The general definition for a client is a device that receives information from servers on a network. And the general definition for a server is a device that delivers information. These, of course, are slightly gray areas because sometimes your client is providing information to other clients, and sometimes servers are actually going out and requesting information. But generally speaking, the primary purpose of each of these is either receiving or delivering information. Network interface cards, which also have been called network cards or network adapters, allow various hardware devices to operate on the network at layer 1 and 2. And like I said earlier, while they're commonly built into motherboards, you can add additional network interface cards if necessary when you have an expansion slot on a desktop or a laptop. When we have a network interface card that operates on the Ethernet protocol, that particular card contains a unique MAC address, which stands for Media Access Control. So your hardware actually has a unique address that doesn't change over time. Your device will get assigned something like an IP address at a higher layer of the network stack, but the MAC address is something that stays static. For wired networks, there are a variety of different cable choices that we can make. Most modern networks are going to be using either Category 5 or Category 6 twisted pair, which allow for speeds up to 10 gigabits per second. Some local area networks have transitioned to fiber optic, which would allow for up to 100 gigabits per second, but this is still not that widely adopted. The devices that connect our various clients and servers together are called hubs or switches. They link the different cables from different devices to each other, sometimes even allowing for a transition from one type of cabling to another. One of their primary features is acting as a repeater, where they receive a signal and then they rebroadcast that signal at full strength to the next device on the network. When we're dealing with a wireless network, the device that receives the radio signals and then sends the radio signals is called an access point. Many access points receive power from a regular wall jack, but some access points use power over Ethernet. So they're actually receiving their electrical signal for data and also their power from the same Ethernet cable. And this makes the positioning of these devices much more convenient. For most modern clients and servers, the network operating system is built into the overall operating system. If you're used to using Windows on your laptop or you're used to running OS X on your Apple laptop or desktop, you are operating in an operating system that has a network operating system built right in. And it is so well integrated that you probably don't have to do much in the way of configuration. For some older devices, you might have had to install additional network functions using something like Novell NetWare or other software that is built to support the network operating system, but that's becoming less and less common. The most common features of LAN software is to provide things like directory services, so you know what sorts of resources are available on your local area network, or provide network profiles to set up what kind of user you are on the network and therefore what sorts of resources you have permission to use. Wired Ethernet is the only standard worth talking about in today's modern local area network environment. And the standard that we use is the IEEE 802.3 standard. You're probably familiar with 802.11 if you've ever configured a wireless network, but you probably haven't seen 802.3 before this class because it is something we've used for decades for our wired Ethernet. This was originally developed by Xerox and standardized by a consortium between Xerox and Intel and Digital Equipment Corporation. And it is a layer 2 protocol, but it does have some requirements of layer 1 as well in order to operate correctly. When we talk about our local area networks, it's important that we discuss our topology, both in terms of how it is logically operating and how it is physically configured. And sometimes these are the same, but sometimes they're different. So we're going to talk a little bit about the original type of wired Ethernet versus the current version of wired Ethernet and how the logical and physical topologies changed over time. One of the earliest network devices we used on wired Ethernet was called a hub, and this allowed us to pursue what's called shared or traditional Ethernet. Each device was physically connected via its own wire to a hub, so its physical topology was actually a star, where every device had its own separate connection to the hub. However, from a logical standpoint, a hub behaves like a bus, where all of the devices act as if they were connected to the same circuit, even though physically they are probably not. What that means from an information standpoint is that every device on a hub-based Ethernet wired network receives every single signal. So for example, if a hub-based Ethernet sends a message from computer A directed for computer C, the hub which receives that message acts as a simple repeater. It doesn't actually address the message to any specific device. It simply receives that message and then broadcasts that message to every device that it is connected to, even back to the origination point. What this requires is that every device that receives the message look at the message and determine whether the message is meant for them. If not, they discard the message, and only the client that was meant to receive the message will actually then use it. You can imagine that this is not a particularly efficient way of using a network. It takes up a lot of bandwidth, it's particularly noisy, it definitely has major security issues because devices are constantly receiving messages that aren't actually meant for them, and in general, this is just not the best way of operating our network. So the follow-up to shared Ethernet was switched-based Ethernet. And this is replacing the hub, which acts as a simple broadcaster, with a switch, which uses MAC addresses at layer 2 to specifically address a message to the specific destination and not broadcast that message to every other device on the network. So switches read destination addresses on the frame at the Ethernet layer, layer 2, and then they direct the message to the specific circuit where that message is meant to be delivered. This allows us to remove some of the collision issues that we had in earlier structures. It improves security quite a bit. It reduces the amount of overall bandwidth on the network. And the physical topology now matches the logical topology, where every device has its own dedicated circuit between it and the network device. If our computer A sends a message for C, that message would be received by the switch. The switch would examine the destination address at layer 2 and then send that message specifically to computer C. B and E and D are left out of the equation entirely, which means they don't have to deal with messages that aren't meant for them. We don't have security issues. We don't have additional wasted bandwidth. You can imagine this is a much more efficient way of operating a network. The way switches typically operate is they learn MAC addresses that are associated with a specific physical port by reading the source address on a frame. So if I connect my computer to a switch and then I send it a packet of information, it's going to see my origination address associated with that frame, and it will learn what my hardware address is by that received message. If the switch finds the appropriate destination address, it will forward it accordingly. If not, it might actually have to resort to acting like a hub very briefly, where it broadcasts a frame to all devices and waits to see if the appropriate device then responds accordingly. This slide shows the various devices that are connected to a switch with their MAC addresses and their associated physical ports. So computer A is plugged into port 1 on the back of a switch, computer B plugged into port 2, etc., etc. If a message comes from computer A, the switch will learn its Ethernet address from that particular message, and then it will send a message to B or C or D if it knows their MAC addresses. If it doesn't, it will broadcast to all the devices on the network and wait for a response from a particular device to identify itself and then send the appropriate message. In addition to only sending messages to the appropriate destination, switches can manage incoming packets in a variety of different ways. One way of managing an incoming frame is store and forward, where the switch waits for the entire frame to be received, uses some sort of error checking algorithm to check to make sure the frame is without errors, and then sends the complete frame to its destination. This does allow for fewer errors, but it does also cause some slowness in the network. If your priority is speed, you might pursue cut-through switching, where the moment that the frame is transmitted and we receive the destination address, we start sending the bits of that frame to its final destination without doing any error checking. This allows for very low latency. Messages will be sent very quickly, but it is possible that some of our capacity will be wasted because we're sending messages that have errors. A compromise between these two methods is fragment-free switching, where the frame is examined up to the first 64 bytes to see if it has any errors, and if it doesn't, then the remaining data is sent through without error checking. So this allows for some compromise between store and forward and cut through. The way that wired Ethernet has pursued its traffic control or media access control is using a series of protocols called CSMACD. Let's work through these various abbreviations in this acronym. The first two letters, CS, stand for carrier sense, and this means that every device that is on the network has the ability to listen to the rest of the network to determine if any other computer is currently transmitting. And a device on this network will only transmit when no other device is transmitting. In the original traditional or shared Ethernet, this was very important. All devices were receiving all messages from a hub, so the network was potentially noisy. Devices would only send a signal when the network was quiet. If another device was currently talking on the network, a device that wants to send a message would have to wait. The second two letters in the acronym are MA, and they stand for multiple access. Multiple devices have access to transmit on this particular network. The last two letters of this acronym are CD, which stand for collision detection. It is possible for collisions to occur on this network, where even if a device listens and waits until nothing is being broadcast, it's possible that two devices start to transmit at the same time. And when that occurs, there will be a collision where the various electronic signals will interfere with one another, but you'll be able to hear that interference. And when that happens, every device that was broadcasting will stop, will wait a random amount of time. Whichever device happened to choose the smaller random amount of time will get to start broadcasting first, and the other device will then have to wait its turn. This technique allows for collisions, detects those collisions, and then responds by random waiting before rebroadcasting. So it is collision tolerant versus collision avoidant. And in the new version of Ethernet, switched Ethernet, this works great because the chance of actually having a collision is extremely low. Every device has its own dedicated circuit to the switch, and the switch is only sending packets back and forth to individual devices when those packets are addressed to that device. so the likelihood of collision is extremely low. This is a good place to pause. Let's continue our discussion of Chapter 7 in another video. Thanks so much for watching. See you next time.